Hey everybody, it's Coach Stoltenberg again, coming with you with the next video in the reactivity unit series. Today we're going to be talking about neutralization reactions, otherwise known as acid-base reactions. We're going to look at a couple of those and make sure we know how to predict the products on them and balance them. And then we'll look at something called a titration and look at the calculations involved in that and get you ready for the titration lab that we'll be doing at some point sometime soon. Alright, so let's get into it. Alright, as you can see, acid-base reactions are also called neutralization reactions because when you mix them together, acids and bases neutralize each other. And when we say neutralize, we're not talking about maybe like your standard dictionary definition. We're talking about pH value. We're talking about pH value getting closer to 7, the neutral level. If in a perfect acid-base reaction, if you have the perfect amount of each acid and each base, then what you should have at the end of that reaction is a completely neutral solution, because all the hydronium ions provided by the acid and all the hydroxide ions provided by the base will actually combine together to produce water. And the leftover ions, the anion from the acid and the cation from the base, will join together and make a salt. Notice not salt, not NaCl, although NaCl is going to be a common one we see. Can be any ionic salt that we're talking about here. So that's an acid-base reaction. An acid and a base neutralizing each other to produce a salt and water. Alright, so let's look at our examples here. I'm going to switch cameras over and I'm going to work this out for y'all. So just follow along with your notes and your examples. Okay, so first one up, we have hydroiodic acid and sodium hydroxide. So we're reacting HI and NaOH. That's our acid and this is our base. So HI plus NaOH yields, well, we know one of our products is water. Every time acid-base reaction, one of our products is going to be water. So I know I can write water. I'm going to write that over here. So what's our other product? It's going to be our salt. So if you're doing these, all you really have to do is think about what you need to make water. You need hydrogens and oxygens, right? So all you really have to do is remove that from on this side. Now I don't want you to actually scratch it out on your example. I'm just doing it here to show you what I'm talking about. So if the hydroxides are gone and the hydrogens are gone, what does that leave us with? It leaves us with sodium and it leaves us with iodine. Those are our two ions that can combine to make our salt. Now when you're doing this, you got to make sure you're doing it correctly, writing your compounds correctly and writing them balanced. So knowing charges is very important. That thing we learned so long ago is still coming back and still important to us here. We know sodium's in group 1. We know its ion is +1. We know iodine's a halogen. It's group 17. It's always -1. So if I'm creating a compound between sodium and iodine, since sodium is +1, iodine's -1, that means we only need one of each. So our other product is NaI. Now always make sure you're balanced. One iodine, one sodium, two hydrogens, one oxygen. That is balanced. Little hint here. If these two have the same, are +1 and -1, then when you're done, it should be balanced. If you've written everything correctly, it should be balanced. If this is a +1 and this is a -1, it should be balanced. So there's the neutralization reaction between hydroiodic acid and sodium hydroxide. Our base produces a salt, sodium iodide, and water, H2O. Alright, let's look at our second example. This one's going to be a little more complicated, but this principle's the same. So our acid, what is that? Carbonic acid. So our acid, H2CO3. Come on. Let's try this again. Carbonic acid. Our base, strontium hydroxide, SrOH2. Okay? This is our acid, this is our base. So what's one of our products going to be? You guessed it, water. And our salt. So our salt is going to be the combination of what's left after water's taken away. So take away the hydroxide, we have strontium. Take away the hydrogens, we have carbonate. Well, what do we know about strontium? It's group 2, so it's +2. Carbonate, polyatomic ion, if you look on the list, it's -2. So +2 strontium, -2 carbonate, 1 of each. So our other product would be strontium carbonate. Again, always make sure it's balanced, but in this case it should be 2 hydrogens here. Oh wait, it's not going to be balanced, I'm sorry, because we're going to have 4 hydrogens on this side, right? Strontium and carbonates are balanced. They're good, but it's the hydrogens and the oxygens that are a little bit off, right? 2 hydrogens here, 2 here, so that's 4 total, and 2 oxygens. Well, if I need 4 hydrogens and 2 oxygens, what needs to go in front of the water over here? Simply put a 2. Probably should write a little bit smaller, give myself a little bit more room here. Now we have a balanced acid-base reaction, neutralization reaction between carbonic acid and strontium hydroxide. There you go. Alright, let's move on. Okay, calcium hydroxide and phosphoric acid. So CaOH2. That's not going to work because I need room in front of it. So I'm going to have to put something there, I promise you. Plus H3PO4, which is our phosphoric acid, yields our salts and water. Alright, so let's try to figure out what our salt is. That's going to be the challenging part. So we have our water, so the hydrogens and hydroxides are gone. That leaves us with phosphate and calcium. Well, phosphate, polyatomic ion, that's -3 charge. Why does the camera keep going in and out of focus? Come on. And our hydroxide, or our calcium, is group 2, so we know that's a +2 charge. Alright, well, so this time they don't have the same charge, so we're going to have to make sure we're balancing this. Let's see if we all can remember the method that we use for balancing ones that look like this. We have a +2 calcium and -3 phosphorus, or I'm sorry, phosphate. Anybody remember? Anybody remember? Yeah, drop and swap it. Drop the 2 behind phosphate, drop the 3 behind calcium, and we get calcium phosphate. So Ca3 PO4 in parentheses, goodness, I need to give myself more room, 2. There's our acid, Ca3PO4 2. I know it's hard to read, I gotta get a bigger board next time. Alright. So now we just gotta balance it. Well, I see 3 calciums here. I only have 1 here, so that means 3 goes here. I see 2 phosphates here. I only have 1 here, so that means the 2 goes here. Alright, so 3 times 2 is 6 hydrogens here. 2 times 3 is 6. So 6 hydrogens here, 6 hydrogens here, that's 12. So 12 divided by 2 is 6. This would be a 1. 6 times 2 gives me 12 hydrogens. 6 times 1 gives me 6 oxygens. So I have 3 and, I'm sorry, I have 6. Just kidding. 2 times 1 is 2, times 3 is 6. There's our 6 oxygens. There you go. There's your balanced acid-base reaction between calcium hydroxide and phosphoric acid. Alright, you have 2 more here. I'm going to give you the formulas. I'm going to want you to work them out. Work them out in your notes, see if you can't balance them, and then, I'm going to either have you show it to me at a later date or show it to me, whenever. So, hydrobromic acid and barium hydroxide. I should make you figure out the formulas yourself, but I'll be nice and give you that. Hydrobromic, hydro prefix means no oxygen, so HBr, and barium hydroxide is barium's group 2, so it's a +2. Hydroxide is -1, so you need 2 of those. Okay, there's your reactants for D. And for E, we have zinc hydroxide. I'm pretty sure zinc is always a positive one. It might always be a positive 2. And then, let's see, nitric acid, that's the acid of nitrate, so HNO3. We'll just go with the assumption that zinc is a +1. I can't remember if it's a +1 or +2. If it's a +1, that makes this one really easy. If it's a +2, it becomes a little bit more difficult. But either way, we'll leave it like this. So there's your reactants for D. There's your reactants for E. Now predict the products and make sure it's balanced. All right. You work on those at your leisure. We're going to move forward with talking about titrations. Moving forward, talking about titrations. So let's flip back over to here. Where are we at? All right. Okay, acid-base titration. This is a very common experiment. It's a experimental method where we're going to take either an acid or base that we know the concentration of, and we're going to use it to figure out the concentration of an unknown, or of an acid or a base that we don't know. So we're going to use it to calculate the molarity of a different acid or base. Now the only way this works is you have to know the concentration of the one that you're doing the titration with. If you don't know the concentration of one of them, then there's no way this works. Also, this only works by titrating an acid into a base or a base into an acid. You obviously can't use an acid in an acid or a base in a base. The reason why you can't use this is because titration experiments require the use of a pH indicator. pH indicator is a chemical substance that will change color when the pH of a solution changes. Now there's a lot of different indicators, and they all can have different ranges of where that's that switch flips from being acidic to basic, and you can see a wide range of colors. We usually use something called phenolphthalein. It gives us a nice bright pink, but there are other indicators that are like dark blue. You have some yellow ones, some dark greens. A lot of different indicators out there. You just got to know which indicator you're using and what that indicator is telling you. Whether it's acidic or basic, what color means what. So once this color change happens, what we do is we use the amount of the acid that's been titrated and the amount of the base that we started with, or vice versa, and we use it in this equation right here. So the M1V1 is equal to M2V2. That should sound familiar, right? That is the same exact equation that we use for dilutions, except this isn't a dilution. And it's not really M1 and M2. It's not initial molarity and final molarity. It's actually the molarity of the acid and the molarity of the base, and the volume of the acid and the volume of the base. We use this to make sure, or we use this to balance this out. It's equivalent because we know when that pH indicator flips, that's telling us that that pH of that solution has flipped, and that's telling us that the reaction has reached an equivalency point. So we can use this mathematically as correctly because that's telling us right when those two things are equivalent. Now, it's not just the math that we're going to be doing. Notice it says we have to have a balanced neutralization reaction and the use of stoichiometry. And I know what you're thinking, oh no, train tracks. Well, really, we're not going to need train tracks here. Or, well, we might have to do a little bit of converting. But it's the mole ratio that becomes important. And we'll look at some examples of that right now. All right, so let's look at our first three examples here. So let me switch cameras again. All right, titrations. Okay, says if it takes 54 milliliters of a 0.1 molar NaOH solution to neutralize 125 milliliters of an HCl solution, what is the concentration of the HCl? All right, so first thing is first. Absolutely first thing you got to do is make sure you have a balanced chemical reaction. This one is this is like your stereotypical acid-base reaction, sodium hydroxide and hydrochloric acid. So HCl plus NaOH, and this one's going to be pretty simple. We get our water, hydrogen and hydroxide gives us our water, and this time our salt is actually salt, sodium chloride, NaCl. And you'll see that it is already balanced. So our mole ratio here between our acid and our base, and that's what we're really looking at. That's the important one. The reason why we need to balance it is to know this mole ratio. It's going to be 1:1, which means our math will be pretty straightforward here. So our equation, MaVb, or Va, sorry, molarity of the acid times the volume of the acid, is equal to the molarity of the base times the volume of the base. All we got to do is plug in the numbers that we have and solve for the one we're missing. So what does it tell us? It says 54 milliliters at 0.1 molar sodium hydroxide. So those are our basis values. We have 0.1 molar and we have 54 milliliters. Notice it's in milliliters. Is that okay? Yes, it is okay because the other side is also in milliliters. Use this much base to neutralize 125 milliliters of our acid, and we're solving for the concentration of that acid. So in the end, this is pretty straightforward. Multiply here, 0.1 times 54 is 5.4, 125x. So divide both sides by 125. So our molarity will be 5.4 divided by 125. 0.04, let's say 0.043 molar HCl. There you go. That's simple. First step, make sure you have a balanced chemical reaction. Second step, use the titration equation, which is essentially the same as the dilution equation. Plug in your values for your knowns, the molarity of your base in this case, and the volume of the base, and the volume of your acid, and then solve for what you don't know. In this case, we're solving for the molarity of the acid. Pretty straightforward. Very simple. Always make sure you have a balanced reaction first. You'll see why in a second, because that mole ratio is very important. All right, let's look at the next example. All right, so this time we have 50 milliliters of potassium hydroxide, and we're neutralizing 125 milliliters of sulfuric acid, H2SO4. All right, so like I said before, balanced reaction first. So our base, potassium hydroxide. Our acid, H2SO4, sulfuric acid. All right, well, we know we have water. That's a given. Potassium sulfate is our other product. Well, potassium is group 1, right? So that means it's +1. Sulfate is -2 polyatomic ion. So when we're doing this, we have to have 2 potassiums, and that becomes real important. If I just write this as KSO4, then it's balanced and I don't really have any issues. But in the end, my math wouldn't be correct. So now I have 2 potassiums here. So that means I have to put a 2 here. That gives me 2 hydrogens, 2 here, so 4 total. So I'll put a 2 here, and now it's balanced. Really, this 2 here is not very important, because we're not really concerned about this mole ratio on this side. We're concerned about the mole ratio here. All right, so what does this mean? We have a 2-to-1 mole ratio. 2-to-1 moles of our base to 1 mole of our acid. So for this reaction to go to completion, for it to go to a neutral point, I have to have double the amount of moles that I have on my acid. So what does this mean with our equation? Well, let's think about it. All right, so the equation is molarity of the acid times the volume of the acid is equal to molarity of the base times the volume of the base. Well, we know this is a 2-to-1 ratio. We have to have double the amount of moles of potassium hydroxide than we do acid. So what does that make you think we need to do down here? Think about it, think about it. And I bet some of y'all have come to the conclusion that we need to double this. You're right. But which side do we double it? A lot of y'all want to double this, because I'm saying you need 2 times as many moles of the base as you do the acid. So times this side. Well, remember, our X is over here. So if we're solving, actually our X is over here, but if we multiply this times this side times 2, that's going to mean that whatever our X over here is doubled. So what we have to do is multiply it on the other side. This side is the side that gets multiplied by 2. So whatever this is times 2 ultimately will give us the right answer. So I don't know. Every year I deal with this. Every year people think that we have to, it's opposite of what it actually is. So I don't know. Maybe just do opposite of what you think it is. If it's a 2-to-1 base to acid, that means you're multiplying the acid side. If it was 2-to-1 acid to base, that means you're multiplying on the base side. This time we're multiplying this side by 2. So let's plug in our numbers that we have here. So let's see, our base 50 milliliters and 0.5 molar. All right, so Molarity of the base, 0.5, 50 milliliters. Volume of our acid is 125, and we're solving for the concentration. So 125 milliliters times 2. All that times 2. So here we have 2 times 125, so 250x. 0.5 times 50, what is that? 25? Half of 50 is 25. Divide both sides by 250. X is equal to 0.1 molar, and that is potassium hydroxide. Now, did we do this right? We have 0.1 molar potassium hydroxide. Did we do this right? What do y'all think? I'm sorry, not potassium hydroxide. Solving for the molarity of acid, aren't we? Come on, Stoltenberg, get it together. Sulfuric acid. Well, let's do some quick math here. So I need to have double the amount of moles of the base that I do acid. So if I 0.5 over 1 is equal to x over 0.05. So this would give me the number of moles of my base. So 0.5 times 0.05. I have 0.025 moles of my base. Alright, so if our concentration of our acid is 0.1, that'd be 0.1 moles over 1 liter is equal to x over 0.125. 0.1 times 0.125, enter, is 0.0125. So that's the number of moles of our acid. Well, guess what? 0.0125 times 2 is, you guessed it, it's 0.025. So we have double the amount of moles of our base than our acid. You don't have to do that. I'm just showing you that that's the way the math works. Double the number of moles of my base compared to my acid. That's what this balanced reaction is telling me I have to have. So that's why we have to multiply this side by 2. And that's why it's mathematically correct to do so. This, however, is our final answer. This stuff over here, I'm just showing you. 0.25 moles of the base and 0.0125 moles of the acid. Alright, that was kind of convoluted, I know, but rewatch it, you'll figure it out. Alright, one more practice problem and then we'll be done. Okay, 0.25 milliliters of 0.05 HCl, 345 milliliters of NaOH. What is the mass of NaOH used? Oh, it's a little bit different, but the beginning of it should be familiar because it's basically the same problem as number 1. So let's take this and plug it in. Let's write our reaction. HCl plus NaOH yields NaCl and water. We know this is a 1-to-1 ratio here. 1-to-1 ratio, real simple. Oh, gotta get it on camera. Alright, so Ma, molarity of the acid, times the volume of the acid is equal to the molarity of the base times the volume of the base. This time we are given the molarity of the acid and the volume of the acid. We're solving for molarity of the base. So our X is here this time. Our volume of the base is 345. Our molarity of our acid is 0.05. And what was the volume again? 25 milliliters. Oh, this is going to be some weak base right here, man. Alright. So first thing we need to do is figure out what the molarity of our base is. So 0.05 times 25, 1.25 on this side, 345x on this side. This is going to be some really diluted base here. Divide both sides by 345. And the molarity of our base is 0.0036 molar NaOH. Alright, so if this is just an acid-base question, a titration question, this would probably be where we would stop. We would say this is the answer. But that's not just what this is. This is also a solutions question, because it's asking us how many grams of this we need. Well, again, that's making us think about information we've already learned, making us reuse information we already know. So that's really a totally different question than the titration portion. But it's also something you should know how to do. Anytime you're given a concentration, set it up as a fraction. This one is 0.036 moles over 1 liter. We are making 345 milliliters, so 0.345 liters. And we want to see how many moles that is. So cross multiplying 0.0036 times 0.345 means we have x is equal to 0.0012 moles. Alright, now we have the number of moles. You guys have been doing this long enough that you know you can always take moles and convert them to grams using good old molar mass. In this case, molar mass of sodium hydroxide is 40 grams per mole. So 0.0012 times 40. And look at that. You don't even need, I don't even have a scale that can measure this much. 0.048 grams of NaOH. There you go. That is technically the final answer to this question. I would never ask you a question this difficult on the test. But again, I like showing you these kind of questions in your practice problems because it shows you that not only do you need to not let go of past information, but that any question that I ask you, no matter how complicated it might seem, you have the methods to solve it. You just need to figure out what the steps are to get there. Alright, that's going to do it for this one. Look for the next video. Will be a titration demonstration to get you ready for the titration lab. Alright, have a good one. Later.